This is the budding light of hope and knowledge, the delight of Sri Prakash Educational Institutions, spreading academic brilliance in all directions.
Welcome to Sri Prakash Educational Institutions online video content. This is a video on derivation of equations of motion, the fifth volume in motion chapter from 9th standard physics, and myself T. Vinod. Instructions to follow. Be ready with your textbook, notebook and pen. Watch and listen to the video carefully. Jot down all the important points in your notebook. In today's agenda, we will learn the word of the day, recite the previous knowledge from graphical representation of motion, learn the equations of motion, derive these equations from velocity time graph, and summarize the content at the end of this video. Word of the day. Derive. It's a verb. Meaning, the source from which something is derived. Development of a theorem. Conjugation. Derive, derived, derived, deriving, derives. Usage. This video describes the derivation of equations of motion. It is not surprising that I derive my distinct eye color from my parents. Learning outcomes. Students will be able to apply the concepts learned in graphical representation of motion, understand the equations of motion and their importance in numerical applications, learn to derive equations of motion from velocity time graph. Equations of motion. There are three equations for the motion of a body moving with uniform acceleration. The first equation is V is equal to U plus AT. This equation gives the relation between velocity and time. The second equation is S is equal to UT plus half AT square. This equation gives the relation between displacement and time. And the third equation is 2AS is equal to V square minus U square. This equation gives the relationship between velocity and displacement. Derivation of first equation of motion. V is equal to U plus AT. For this, we will consider a velocity time graph of a body that moves under uniform acceleration. So if a body is under uniform acceleration, you already know that it will be a straight line having a constant slope with the time axis. Here it is the same, but very important thing to note is this body is not initially starting from rest but has an initial velocity. Let us make some markings on the graph for easy identification. The body has initial velocity u, so which is represented by OA, that is equal to CD on y-axis. Then the body accelerates uniformly, and in time t, it acquires final velocity which is equal to OE, and that is also equal to BC on y-axis. Initial velocity at time t is equal to 0 is represented by OA on y-axis. The final velocity V at time t is equal to BC. The velocity time graph for uniformly accelerated motion is given by the straight line AB. Acceleration of the body is equal to change in velocity by time taken is the formula for acceleration. From the graph we can calculate the acceleration by finding the slope of the line AB, that is change in y-axis by change in x-axis. On y we have BD and along x we have AD. So A is equal to BD by AD. BD can be also written as BC minus DC by AD. From the velocity time graph, we have BC which is equal to V, and DC, that is equal to OA, is equal to U, and then we have AD which is equal to OC, that is equal to T. By substituting these values in the above equation, we have A is equal to V minus U by T. When we send T to the other side, it multiplies with A. AT is equal to V minus U. By sending minus U to the other side, it becomes plus U, which is V is equal to U plus AT. This is the first equation of motion. Derivation of second equation of motion. S is equal to ut plus half at square. For a body under uniform acceleration, suppose it travels a distance s in time t. The distance traveled by the body is given by the area under velocity time graph. In order to find the area, we split it into two geometric shapes. One, the rectangle, the second one, triangle. We find these areas separately and add them to get the complete area under the velocity time graph. Distance traveled, S is equal to area of a right triangle ABD plus area of rectangle OADC. We know that the formula for area of a right triangle is half base into height, and then for rectangle it is length into breadth. From the graph, half AD is the base and BD is the height, and OC into OA will give us the area for the rectangle OADC. Let this be equation 1. From the figure, AD is equal to OC is equal to T along the x-axis. We have BD which is equal to BC minus DC. Since BC is V and DC is U, so BC minus DC will be equal to V minus U. From the first equation of motion, we have V is equal to U plus AT. Substitute this value of V in the above equation. That is U plus AT minus U. Plus U and minus U get cancelled and BD is equal to AT. OA is equal to U along the y-axis. Substituting these in equation 1, we get S is equal to half T multiplied with AT plus T into U, which is equal to half AT square plus UT. Rearranging this, we will have S is equal to UT plus half AT square. This is the second equation of motion. Derivation of third equation of motion. V square minus U square is equal to 2AS. For a body under uniform acceleration, suppose it travels a distance s in time t, we can get the distance by finding the area under the velocity time graph AB, which is equal to the area of trapezium OABC. Distance traveled S is equal to area of trapezium OABC, which is equal to half into sum of the parallel sides multiplied with the perpendicular distance, which we call it as height. S is equal to half. The two parallel sides are OA and BC, and the perpendicular distance is OC. Substituting the values of OA, BC and OC in the above equation, we get S is equal to half into U plus V multiplied with T. Let this be equation 2. We know that from the first equation of motion, V is equal to U plus AT. From this relation, we can derive another equation for time. T is equal to V minus U by A. Substituting the value of T in equation 2, the equation becomes S equal to half U plus V. In place of T, we are substituting V minus U by A. Sending A and half onto the other side, the equation becomes 2AS is equal to U plus V multiplied with V minus U. So rearranging the above equation, 2AS is equal to V plus U into V minus U. So it is in the form of A plus B into A minus B, which is equal to A square minus B square. Applying the same rule here, we have 2AS is equal to V square minus U square. This is the third equation of motion. Uniform circular motion. When an object is moving on a circular path with a constant speed, its motion is said to be uniform circular motion. Example, the moon revolving around the earth. Another example, an artificial satellite revolving around the earth.
Uniform circular motion. If a body performs motion with constant speed along circular path, its motion is called uniform circular motion. Here, note that speed remains constant, not velocity. Direction of velocity of a body in uniform circular motion is different at each point on the circular path. On the circular path at any point, velocity is in the direction of the tangent drawn at that point. Do you know what is tangent? Let us know this. A line lying in the plane of the circle, which intersects circle in only one point, is known as tangent to the circle at that point. Line segment joining the center of the circle and the point of contact of tangent and circle is always perpendicular to the tangent. As shown in figure, consider a body performing uniform circular motion along the circle of radius r in anticlockwise direction. When this object is on point A, B, C, D and E, direction of velocity are shown here. Here, note that the direction of velocity is different at different points, but as it performs uniform circular motion, speed is constant. Therefore, V1 is equal to V2 is equal to V3 is equal to V. If the body completes one revolution along circular path in time t, its speed can be determined as follows. V is equal to total distance covered upon time to cover distance is equal to length of the circular path upon time is equal to circumference upon time. V is equal to 2 pi r upon t. Here, V is also known as linear speed of the body performing uniform circular motion. Can uniform circular motion be considered to be motion with uniform velocity? Think over it. Remember, here magnitude of the velocity remains constant, but the direction of velocity constantly changes. So, in fact, uniform circular motion is accelerated motion.